Mm-hmm. All right, so the next thing to talk about is metabolism. Students tend to have a little bit of difficulty with this particular thing. So here's the question that I'll be asking you is, here's a drug, it's metabolized by such and such an enzyme. Here's another drug that either induces or inhibits that enzyme. What do I do with the dose? What happens to the patient? Okay, so let's talk about that. Now, except for some of the drugs that have to do with the brain and neurotransmitters, most inactivation of drugs is in the liver, and in the liver you have these banks of enzymes that break down different drugs or toxins. So they either break them down into metabolites which have less activity than the original drug. Or sometimes what they do is they add little charged groups to the drug. So they might like take some drug molecule and just stick some positive or negative charge on it so that the drug is more water soluble so it can be excreted into urine more easily. But the drugs that I want to talk about the most right now is Cytochrome P450 enzymes. In Hittner, they refer to this as the DMMS system, which I've never seen DMMS anywhere else. It's really my only criticism of, sorry, if it jiggles, just, I don't know. You guys know about phones. I can pretend I don't know. So the Cytochrome P450 enzymes, everyone calls them that. Nobody calls it DMMS except for Hittner. He's the only one. And the Cytochrome P450 enzymes are sort of like, in the last 10 years, have become a bigger and bigger deal in terms of explaining why some drugs have interactions. So each of these enzymes, there's a ton of them, but some of them are very, very commonly the enzymes that break down a drug, and there's CYP1A2, 2C9, CYP2C19, CYP2D6, CYP2D1, and CYP3A4, 5, 6, and 7. So there's all these, that's the name of the enzyme. That was the best that people could come up with. All right, and you'll find on D2L and also on my website, which is now, if you go on my website or on D2L, there's a couple of tables which have these P450 drug interactions on them. I like this one. This is the Aschenbrenner one. You can look at both of them, whatever you like, is fine. And what these tables show is for each of the enzymes, right, which have these sort of not very fancy names, you have the enzyme, the drug that it changes, its own substrate, and then what drugs either inhibit the enzyme or induce the enzyme. All right, and so here's all the information for CYP1A2, here's all the information for CYP2C9, and that's the idea. Now, nowadays, luckily, there's some drug interaction apps that kind of have this information there, so please don't try to memorize this, that would be insane, right? Especially because these tables change all the time. They get bigger and bigger and bigger as new drugs are sort of figured out which go with which enzyme. Now, on a exam or a quiz, I'm going to probably give you a little mini table. So what I've done here, if you can't see it, don't worry about it. You can look at it later. But it's just, you know, I'll give you the enzyme, the substrate it breaks down, the thing that inhibits it, the thing or things that inhibit it, the thing or things that induce it, and so forth. So this table is set up a bit like the table in the Indiana University table. So just so it doesn't matter which format the table is, the thing that counts is that you know how to figure out the information, and that is always going to be, the enzyme is always going to be called CYP something, and then the substrates are whatever that enzyme breaks down. So I always think of enzymes as sort of being like little Pac-man, because I'm from the 80s, so to me, anything that breaks anything down is like Pac-Man, right? So you have Pac-Man happily munching away at some substrate. So somebody was asking me earlier this week, you know, very confused about the idea of a substrate and a ligand, an enzyme and a receptor. So an enzyme breaks down a substrate, and a ligand binds a receptor. Sorry, I'm taking a little bit of a it's a side quest here to make sure I have this right. Okay, so you can have the same molecule be a substrate for an enzyme that is a ligand for a receptor. It's kind of like how I'm a sister and a mother, right? It's like I'm still the same person, it's just my relationship is different in different situations. So like you can have acetylcholine getting broken down by an enzyme, but you can also have acetylcholine binding the receptor. An enzyme changes its substrate, a ligand does something to the receptor so that it has an action. Okay? I want to bring it up. Somebody was asking about it yesterday. Okay, so if we have any drug, the enzyme is going to break it down in some way, and then there might be other drugs that either induce the amount of enzyme or inhibit the amount of enzyme. All right, so I think probably the example that students that most people are familiar with, even if you don't have personal experience with it, is the idea of alcohol. So alcohol is a drug, okay? And alcohol is a drug that's a little bit unusual in that it induces its own enzyme. So even if you've never had any experience with alcohol, if you saw Raiders of the Lost Ark, there was a scene where two people were trying to drink each other under a table, which means that you put a table down and you have two people, and each one is given the same drinks until one person like dies or passes out or something. So if you took like someone like me who never drinks ever, and you took somebody like my grandmother, who I once came into the kitchen and she had a bottle of, I guess, ginger vodka or something. She was drinking it like this, like drinking it like a Pepsi. Unbelievable. And died of Alzheimer's, didn't even die of a liver problem. Maybe she's like Rasputin, couldn't kill her. So if you take me and my grandma, and you put us down at a table, and you start feeding us shots, you know, we both get a little bit buzzed from the first drink, and then after that, she'd just be drinking and chatting, and I would be like naked and dancing with a lampshade on my head, or dead, one of those two things. And you'll be shocked at how much people drink when you start taking social histories of patients. You're like, I couldn't believe, you won't be able to believe that the human body can even fit that much alcohol into your stomach in a day. It's unbelievable. People are like, oh, I drink 4 or 5 cases of beer. Like, what? It's crazy. So anyway, so my grandma, again, she's gonna be fine. I'm gonna be dead. That's because she, over time, has induced that her enzyme that breaks down alcohol breaks that down over time. So, all right, so you see news items about this every year, especially in the fall. That some poor fraternity guy was in hazing, and they were giving him lots of alcohol, and he died of alcohol poisoning because he never drank anything before. And There was a singer, Amy Winehouse. She died, a couple of years ago. And internet reports have been varied, but most of the time I've seen that she died of alcohol poisoning, which is very consistent with her story, because evidently she was quite a heavy drinker and then decided to stop drinking and didn't drink for a while, and then went back, for some reason decided to drink again, and went back and drank the amount she was used to drinking before, and then was poisoned by it, because over the time that she hadn't been drinking, her enzyme levels went back down to normal. And this is evidently quite a common problem also in Alcoholics Anonymous, that its members, you warn people, if you fall off the wagon, and that to me, if you start drinking again, don't drink the amount you used to drink, because you can die of alcohol poisoning. Right? So that's an example where, you having that exposure to alcohol every day, induced the enzyme. So now just instead of one little Pac-man, you have tons of little enzymes just chugging away, chewing up all the alcohol. And this can happen with prescription drugs as well. Right, so let's do an example here. Okay. Is this an inducing one? Yes, okay. So St. John's wort, I've made a little table here too. St. John's wort is a natural drug. And I always say natural because there's no legal word. Natural is not a legal word, so I can say this is natural because that doesn't mean. So, but it is a natural herb that grows on the planet. That is often used for mild depression. It's been through clinical trials. It definitely works. But this is a natural drug that is an inducer of CYP3A4. So if I look at my little chart here, I can see that St. John's wort induces CYP3A4. It also induces CYP2C9. It actually induces a lot of enzymes, lots of problems with drug interactions. If I have a patient who's maybe has an estrogen receptor positive breast tumor and is taking tamoxifen, CYP3A4 breaks down tamoxifen, meaning that tamoxifen is its substrate. So if the patient on tamoxifen starts taking St. John's wort without telling you, which happens all the time, what we need to do about the dose of tamoxifen. So we're going to assume the patient continues to take the amount of tamoxifen that they used to take. All right, so that has not changed, but they started taking St. John's wort. What's going to happen? A, the drug will be more effective. B, the drug will be less effective. C, no change. Okay. Okay. All right, I've got about a 50-50 split. The second row is still thinking. No? The good news is you have a 1 out of 3 chance of guessing right. On tests, do not leave anything blank. You do not get penalized for guessing. Don't guess with a patient. You guess with all right, so you guys are about half and half A and B. Okay. The answer here is that the tamoxifen will be less effective because if the St. John's wort is, and it's like I got a million pens I never heard of. If the St. John's wort is inducing the enzyme, it means you have way more enzyme around. All right? Which means when that tamoxifen hits the liver, it's going to get broken down very quickly. All right? So now the tamoxifen is going to be less effective. So you have patients being taken care of for cancer. The cancer it was responding really well initially to the treatment, and suddenly it's coming back. Sometimes that's because of other things like this. And you have to be careful when you're with patients because there's a perception in the media, and therefore in the population, that doctors and nurses don't want you to know about cures, and they are very against natural drugs and vitamins and things like that, which is not true. So when you are doing a patient drug history, you can't just be like, do you take any supplements or vitamins? Like, that's not the way to ask that. Say, well, are you taking anything else, anything that might be boosting your energy, or because it's important, it might interact with the drug. You have to find a way to ask that's not threatening, which takes some time. All right, so here's another patient. So we have a patient, Steve. All my patients seem to be named Steve or Bob or John or Mike or something. He is taking an anti-seizure drug called phenytoin. So he decides he has heartburn and he starts taking Tagamet, which is over the counter. So these are both metabolized by the enzyme 2CYP2C9, and we want to know what happens to the level of phenytoin. So in this case, phenytoin is the substrate, right? Because that's what we're interested in. What is happening to the level of phenytoin, right? So when we look at the table, we're looking for phenytoin in the substrate column or row, depending on the chart you're looking at. All right, so if cimetidine inhibits that enzyme that breaks down phenytoin, then what happens to the level of phenytoin if you imagine the patient's still taking the same amount of drug? Okay, so this time we got a little bit more consensus that the answer is B. And the reason is, which is true, because if we're doing a metabomet, right, so here's our happy enzyme chewing up all the phenytoin, and now what you've done is you've inhibited the enzyme. So the amount of enzyme goes down, and now look, he's sad. I should take it, I'm a goofball. Anyway, so you've inhibited the enzyme. So now the enzyme is no longer breaking down this substrate. And the patient keeps taking his dose every day, a couple doses a day, and so the levels rise. Okay? So there's a bunch of different ways I can ask this question, and the one before too. I can say, what happens to the level of phenytoin in the bloodstream? Or I can say, what do you do to adjust the dose? Right? So if the level's going to increase, what do you do to the dose? You decrease the dose. Okay? Or I can ask, what's going to happen to C? Right? So if the level increases, he might be getting toxicity from the phenytoin. It can cause arrhythmias. Right? So that's a problem. Or in the other case, if he was taking St. John's wort, which also induces the 2C9 enzyme, in that case, the level would be going down and he would have a seizure. Right? So that's another thing, right? You give the drug, you're looking at the patient, and then you see what happens to him, and then you have to figure out why it happened. Right? So I think this is confusing to students because I can ask it in so many ways. You're inducing or inhibiting the enzyme, okay? So higher enzyme, lower substrate. Right? Lower enzyme, higher substrate. But you also have to change the dose. So if the dose goes down, you have to increase the dose. Right? If the level goes up, you have to decrease the dose. So you see how there's like arrows going? So it's one of those things like the best way to learn it is to just understand about the enzyme being increased or decreased, because if you just remember it goes up or down, like on a table, then that won't stick with you. All right, I see some people looking confused, other people looking impatient.
You have a video on this, right?
I don't remember. I can make one, but I also have on the D2L. I have a practice problem. So I have a practice problem for this, and I have a practice problem for half-life. And I think there's a practice problem also on one of the sheets I have you look at next week. Right. So it's one of those things you just got to sort of like work through it a few times, and then you get it. The most common mistake people make is they think when I say it's inducer, they think I'm inducing the level of the drug, which is not the case. I'm inducing the enzyme. That's what I'm inducing. All right, so we already talked about first pass metabolism. All right, now here's a tricky question. We go till 9:50, is that right? Okay. Everyone's like, yeah. Sorry. Maybe I should start bringing donuts. That might help. I also look to make sure no one has a donut allergy. All right, so here's a tricky question, okay? And this is now a drug metabolism question, nothing to do with enzyme. All right, so I'm taking care of a patient named John. My dad's name is John, so John. That has an order that reads codeine 30 mg PO Q4H PRN. So 30 milligrams PO is by mouth and swallowed, right? Q4H every 4 hours. PRN
As needed.
As needed. So if the patient asks for pain medication, that's what you can give. Right? Don't get PRN mixed with PR, which is per rectum. You don't want to be trying to stick codeine up someone's mouth. It's not going to work out. All right. So codeine is another one of these opiates, like hydrocodone was, and at high doses can cause the patient to stop breathing. All right. So too high of a level of codeine, you stop breathing. Too low of a level of codeine, no pain relief. All right. So this patient, John, he has terrible liver failure, waiting for a liver transplant. All right. And so codeine, because it's a prodrug, it gets activated in the liver. All right. It gets turned into morphine. I think I was mentioning it during the break. That codeine is transformed in the liver to become morphine, and that's how it works. So if I give the patient his dose as written, he'll either not get pain relief, stop breathing, or thank you and smile gratefully. So which do you think that will be? So this is a little bit of a trickier question because codeine is not broken down in the liver, it's actually activated in the liver. All right, I have about 60% consensus that it's B, but it isn't. The answer is A. All right, so here's a situation. Now, don't worry about this, okay? So remember when we talked about first pass metabolism, the drug has to go through the liver. If you give an oral drug, that the drug is always, is always going to go through the liver before it gets to the general circulation. So if this drug has to be activated in the liver, if it doesn't have any activity on its own, and it only works when it's activated, then if you have no liver, the drug isn't going to work. Does that make sense?
Can you say that again?
So the drug, let's imagine that codeine has zero activity on its own. It absolutely does not relieve any pain. Okay, the molecule codeine. It goes into, you swallow it, it passes through the liver, and the liver activates it to morphine, which is a great pain reliever, right? But codeine on its own, in this situation, has no activity. So if you swallow the codeine and it gets absorbed and does not get activated, it just flows around your bloodstream, but it doesn't bind any receptors, it does you no good. So the only way to get action from the codeine is to have the liver activated. Does that make sense? It's like a little backwards thing. So that's one of those things where, again, you can't just memorize up and down and higher and lower numbers. You have to understand it, or else questions like this make no sense. Yes?
So because he has liver failure, codeine won't be activated.
Right.
So then why take it?
You wouldn't.
Right. Okay.
Right. But it's July 1st and the intern wrote the order. And you have to realize, well, that's probably not going to work.
Gotcha.
Or if he's only got like 5% of his liver left, then he's going to have to have a massive dose of codeine, which you'll have to slowly titrate up, just so you don't accidentally make him stop breathing. And then once you figure out what the dose is, then the pharmacy will call you and say, you can't possibly want this high dose, and it's a big pain, so you just give it to him. It's just easier to give it IV. But sometimes you have patients that take drugs, they take drugs as outpatients, they need to take a pill. What are you going to do? You have to give him a drug that's going to work on its own. It doesn't, that is not a prodrug. Does that make sense? Yeah, but it's like a backward situation, right? So now you're seeing why the nurses have to do so much paperwork. Because you have to figure all this stuff out. Do you have a question? I thought I saw you. No? No?
Right.
Oh,
One more question.
yes.
I just want to know, how do you know which drug is activated by the liver and which one is metabolized in the liver?
You're supposed to memorize it. So you won't have to memorize that for me, but in the future, you're going to have to learn this kind of stuff. Because, drugs that are like not metabolized by the liver but only excreted, so like as long as the drug is in your bloodstream, it's still working. In that case, if you have a patient with crappy kidneys, you have to lower the dose because otherwise the drug doesn't get excreted. So yeah, pharmacokinetics, that's a nursing thing. So that's why you get a blood draw when you first go to the hospitals, because that gives you an idea. Is their liver working? Is their kidney working? Do they have albumin? All these things. Are their electrolytes okay? All those things are going to help you when you're trying to figure out why the patient died or why the patient isn't getting a benefit from the drug. It's probably not very comforting, but there you have it. Okay, and when you're starting out, just so you aren't like totally panicked, when you're starting out, you have like a little book or an app that you can look stuff up on, and you will slowly memorize it. During a day of doing nursing, there's no time to look everything up. So eventually you end up memorizing it all. But when you're starting out, you get to look things up. I think when you start out as a nurse, they have you write up these things called care plans, where you have to look at the patient, look at all their drugs, and then like figure out all this stuff. And when you first start doing that, that's going to take you like 12 hours to do a care plan. But by the time you're in practice, it'll take you 5 minutes to do it. So it's just a process. So don't be too panicked about it. So don't worry too much. All right. So lastly, excretion just means get it out of the body. All right. So again, for the most part, let's assume that excretion is through the kidneys, unless I sort of say otherwise. And a lot of drugs are excreted through the kidneys, but also you get some of the drug excreted in sweat and spit and breast milk. So that's an issue if you have a woman who's breastfeeding. And even poop, it doesn't matter. I mean, if you had drug all stuck in your hand, you could cut your hand off and get rid of it that way. I wouldn't advise that, but that's even a way you could do it. So there's all different ways to get the drug out of your body. But the kidney is mostly in charge of that. So I guess I didn't have a little question. Oh, I feel sad. Oh well, that's okay. So again, kidney excretion becomes an issue when you have patients with reduced function in the kidneys. When you're doing your web assignment, which I highly recommend you work on this weekend, so you aren't having to do it right before the test, I'll send you to rxlist.com and pdr.net. Look at rxlist.com or even drugs.com, and you'll see there's a bunch of tabs, and one of them is clinical pharmacology. Just click on that for a few drugs, just any drug, it doesn't matter, any prescription drug, and click on that and take a look at it, and you'll see it says absorption, distribution, metabolism, excretion, and it says how to change the dose for old people, or for people with crappy kidneys, or for people with bad livers, or all of these things. It's all, for every drug, it's all been figured out. The problem is, for every drug, there's like a 12-page article about this. But it does come over time, I promise. But that was quite a common thing in the 70s and 80s, was that little kids would come in because they'd been poisoned with baby aspirin because they got to the baby aspirin because it tasted like candy. Okay, so aspirin is an acidic drug, right? Or you don't know that, I'm telling you. Aspirin is an acidic drug. So an acidic drug in an acidic environment is lipid soluble, right? An acidic drug in a basic environment is water soluble. So if you want to get that aspirin out of the person's system, and it's too late to pump their stomach or whatever, right? So you want to get that aspirin excreted as fast as possible. What you can do is make the aspirin more water soluble by changing the pH of the blood a little bit. And you can do that a variety of ways. The easiest of which is to just give them a little injection of sodium bicarbonate, good old baking soda, Alka-Seltzer, that stuff. Bicarb is the natural buffer in the body. And you can change the blood pH just a little bit, and that will significantly increase how much of the drug is water soluble and therefore easily excreted. I have a video for you guys to watch about ionization and absorption and excretion of drugs and pH. And at the end of the video, I just have a math problem. And almost nobody looks at the math problem, I'm told by students. I don't expect you to work through it, I'm not going to ask you to do a math problem, but if you look at that, you can, what that math problem shows is that a very small change in pH can have a huge impact on how much of the drug is either lipid soluble or water soluble. All right, so that's the idea there. So if I wanted to, to treat aspirin overdose, you could give them a little bit of sodium bicarb to get that drug out of the system as fast as possible. Aspirin's not good at high doses. All right. Also, there's a drug we're going to talk about later. I hope we're going to get to it, called Amiodarone, which is a heart drug that is excreted in the bile. And bile, if you'll remember, is a cholesterol that is used to help you digest fat. And because amiodarone is excreted through bile, the bile goes into the intestine and then is taken back up and reused. So it keeps getting recycled unless you do something to prevent that. And because of that, amiodarone has a half-life of 2 months, which is quite long. And that's going to have a huge impact on how long it takes for that drug to get out of your body. I'm going to come back to bioavailability in a second. But I want to talk about half-life. Okay, so half-life is the time required for the blood concentration of a drug to be half the level it was when you started, when you stop the drug. Okay, so here's a question. You take a drug that has a half-life of 7 hours. How long will it take for more than 99% of the drug to be out of your system? It's going to be 7 hours, 14 hours, 28 hours, 50 hours. Okay. Yes, right. Okay. Almost all of you have fallen for my evil trick, which is that most of you say 14 hours, because that makes sense, right? Half of it's gone after 7 hours, the other half will be gone after another 7 hours, but that's not how it works. It's actually half of a half of a half of a half of a half. So for any drug, doesn't matter what the half-life is, for 99% of it to be gone is going to be 7 half-lives. So if the half-life is 7 hours, then 7 times 7 is 49. For amiodarone, which has a 2-month half-life, for 99% of the drug to be out of your system is 14 months. I think that's kind of cool. All right, so let's do an example. If I just show you one example of working through the problem, then it'll totally make sense. So To do a half-life problem like this, you have to be able to divide by 2 and use a clock. So, which you'd be surprised, that's the most common mistakes I see are clock or 2 related. And it's not because people don't know, it's they get nervous and forget to. Okay, so let's do an example of a drug. Let's give, say a patient accidentally took 100 milligrams of some drug Monday at 8 a.m. He comes into the hospital because he wasn't supposed to take the drug, and that's a very, say the drug normal dose is 5 or something, 5 hours. So he took way too much, and so you have to figure out how long you have to keep him there under observation until you can release him, and you know you'll be able to release him when only 10 milligrams is left in his body. So you have to figure out, okay, how long is it going to take, how long are we going to have to watch this patient before they're out of the woods, they're out of danger. So, this is how it works. If we start at Monday at 8 a.m., and in this problem, the half-life is 10 hours. So 10 hours after 8 a.m. is what? 6 p.m. on Monday. Half of 100 is
50.
50. Whoop, it's like a 5 in a giant hole. Okay, so 50 mgs is left. Okay, so now 10 hours later is what? 4 a.m. on Tuesday. All right. So now the half-life has to do with this time. It doesn't matter what the starting dose was, because the half-life is only looking at how much is after 10 hours, how much is left compared to 10 hours before. All right. So if 50 milligrams was there at 6 p.m. at 4 a.m., I'll have 25 milligrams. Like, now it makes sense, right? All right. So let's go another 10 hours. So that's 2 p.m. Is that right? I can't ever do math in front of a group. It's like I'm not very shy, but like math, I just can't do. So you'll have to stop me if I screw this up. All right, so let's say that's about, that's about 12 and a half milligrams. All right, we need to get down to 10 milligrams. All right, so now another 10 hours. That's what, midnight? Okay, so how much is left now? 6.25, right? I'll round it up. All right, so keep going. We can keep doing this, right? So now, after another 10 hours, there's what, 3.2 milligrams left. After another 10, that's 10 a.m. Now we're on Wednesday. See where I'm going with this? Yeah? Right, 10 hours later, that's 8 p.m. Now we have 1.6 left. And then 10 hours after that is 6 a.m. on Thursday, which is 0.8, which is less than 1, right? So in order to get from 100% of the drug to 10% of the drug, we had to go about 1, 2, 3, 4, somewhere between 3 and 4 half-lives, right? 1, 2, 3, and 4, 4 half-lives. So the rule of thumb is between 3 and 4 half-lives. Some places you read, I think it's even in my handout, 3.3 half-lives, whatever, is to get 10% of what you started with. And if you go 5, 6, 7 half-lives, then you get down to less than 1% is left, right? So 10% is left here, 1% is left here. And because it's always a half of a half of a half of a half, the percentage is always the same. I can start with 427 milligrams, and to get to 1% left, it's still going to always be 7 half-lives. All right? So that's the trick. And when I say you need to use a clock, it's that everybody's different. Like this is, in fact, this is a nursing watch. You can always tell a nursing watch because it's always divided into 15-second groups so that you can easily take a pulse. I think of it that way. If you're good with digital and you can figure these numbers out, that's fine too. The most common mistake I see when students are doing these problems is that they write Monday, 8 a.m., and then they write 50 milligrams, because like in their head, they're already dividing by 2. So that's the most common mistake I see. So if you're trying to work through a problem and I say, I have such and such amount of drug left, at what point, how long will it take to get to this point of the amount of drug, just remember to start, at the start time is with the starting dose. That's the most common mistake. Okay? I know, it's pretty simple. All right, we're getting to the last 10 minutes. It's very hard to like take in new information in the last 10 minutes. Just I'm going to try to power through a couple of things. These, I think the rest of this handout is fairly straightforward, but let me go over a couple of quick things. The first one I want to go through is the placebo effect, because I think this is in the web assignment, it's definitely on the test. And that's, again, another issue where what your understanding is of the placebo effect as a civilian is different from your understanding as a healthcare professional, all right? So as a civilian, a placebo effect is, I'm going to give you a pill, and I say, this pill is going to make you fall asleep, all right? And then you take the pill and you fall asleep right away, and it turns out what I gave you was just like a little sweet tart. There was no medicine, right? So that's, for the lay person, that's the placebo effect. When you talk about a placebo effect of a prescription drug, sometimes people are talking about that, but more often they're talking about this. So whenever a drug goes through FDA approval, first it's tested out on healthy volunteers just to make sure there's not terrible toxicity. And then it's tried out on patients, right? So when they try out the drug in both situations, usually in a controlled study, you have half the patients get the drug and half the patients get a pill or capsule that looks just like the drug but only has like starch or sugar in it or something, all right? So what you do then is you give everybody the medication and then you give them this like folder. It's a survey. And they have to take the survey every day or every couple of days or something. And the survey says, you know, you took this medication, how do you have any of these symptoms? And then it's a list of symptoms, all right? So it's headache, rash, nausea, dizziness, constipation, diarrhea, all these things, right? And it can be over the course of 2 weeks, it can be over the course of a month, who knows? But that's what happens. And so what they do when they're figuring out if the drug is safe or what the effects are, they look at those surveys and they look at the difference in the surveys from the people who had the placebo, the pretend thing that didn't have drug in it, and the one that had the drug. So the placebo effects here are not that they gave the patient the drug and said, okay, you're going to have chest pain or you're going to have lightheadedness. It's that they took the drug and then they filled out the survey and said different things that happened to them. And you know, just from being a human and being alive, that over the course of a month, maybe you might have a headache, or maybe you feel dizzy once because you didn't eat, or maybe you have constipation. I mean, that just happens, all right? So this percentage here, okay, N is the number of patients in that group, okay? And this is percentage. These are the percent of patients that said they had this symptom. So these people were going to have this symptom regardless, right? It's just if they had taken not any medication, if they had just been living their life, they were, you know, 18% of the people would have had a headache. And in fact, if you look at lots and lots of drugs on our Rx list or whatever, and you look at these kind of tables, you'll see that in most studies, about 15 to 20% of people say they have a headache. It's just like the amount of people that have a headache over the course of several weeks. All right. Now, so if I were to say, well, is chest pain, is that a real effect of the drug? Is it a side effect of the drug, or is it a placebo effect? In this case, you'd say, well, it's a placebo effect because 7% of people are going to have chest pain, and those 7% were going to have chest pain regardless of taking the drug, so that's a placebo effect. It's an effect that has nothing to do with the drug. And here you might say, okay, lightheadedness, 8% had it with the drug, and 6% had it with the placebo. So that means 6% of these people were going to have it anyway, but 2% had the lightheadedness because of the drug, right? And you might say, well, 2%, that's only a little difference. It is only a little difference, but it can be statistically significant. You'll see some trials where the N is 14,000 because it's somewhere like Sweden or Denmark where they have socialized medicine and they know exactly what drug every single citizen is taking. Sometimes you see that. Here, the placebo was 5%. You were expecting 5% of people to be nauseous. Turns out only 2% were it was. So maybe nitrogen would be good for nausea. That's how they find other indications for drugs often, is during this testing. They're like, wow, everybody took this drug, none of them had a headache. This drug must be good for headache. Nitrogen, however, is famous for causing people headaches, and sure enough, way more than 18% of people had headache. So in this case, I would say that angina was definitely a placebo effect. Nausea is definitely a placebo effect, right? If anything, fixing nausea is an effect of the drug. All right, so here, the placebo effect, you can account for all of these people that they were placebos. And you might say lightheadedness and headache might be real effects, the side effects of the drug. okay? Right? And the only other thing I want to point out, and again, this is self-explanatory, I don't think I have to go through it. This is something you can go through on your own. However, there's pregnancy categories and there are drug schedules, two separate things. A pregnancy category is usually released at the time of the drug being released, but of course you can't test drugs on pregnant women. So all you can do is test them on animals. So category C drugs are usually when if the drug caused malformations in animals, the drug is released as category C. Usually with time, things get turned into category D or X because pregnant women take it and then they have babies with deformations, so that's not good. My personal mnemonic is A is okay, X is definitely not. I'm a big Marvel Comics fan, even before the movies, and so I think the X-Men is like mutation, so that's how I remember it. For drug schedules, it's Roman numeral 1 through 5, and to me, the Roman numeral 1 looks like a capital I for illegal. That's how I remember it. So I'm just giving you my mnemonics to help you out with that. And then lastly, there's some common abbreviations. There's tons of abbreviations. These are the ones that I'd like you to be fairly familiar with, right? So that if you see Q4H or you see QID, Q4H is every 4 hours, QID is 4 times a day. That's every 6 hours, right? Just to sort of start learning a few of these, and then when you have to learn more of them, that'll help with that. All right? So please check D2L for the list of what to do for next week. The extra credit for next week will be the other page from Quizlet that I gave you, which is all the drug names, what drug class are they in.